Today we're going to look at perpendicular bisectors. Remember we studied bisectors already way back in chapter 1. If we have a segment, we don't bisect lines because lines go to infinity in both directions. Same thing for rays, but a segment we can bisect. Now we can go like that. That bisects it, but it's not a perpendicular bisector, is it? It's a very special type of bisector called a perpendicular bisector, which has some special properties. For instance, when the distance from here to here and here to here, when those two distances are equal, they are called equidistant. You probably would have figured that out already. Just in case you weren't sure. So we say that C is equidistant from A and B. A and B are the endpoints of this segment. This is a perpendicular bisector. P is a midpoint. And CP is perpendicular to AB. Every point on this perpendicular bisector is equidistant from the endpoints. Simple enough. Kind of looks like that would be true, doesn't it? Well, it is true. And the converse is if, well, you can read it pretty easily. If the points are equidistant, then it is on the perpendicular bisector. And that's probably how your teacher showed you how to construct a perpendicular bisector. Exactly that way, taking advantage of that fact. In other words, you would take your compass, you put one end here, and draw a little arc, and then put another end here, and draw another arc, and where they meet is equidistant from these 2 points here. We'll pretend that's the end of the line. So you draw a line from here to here, and you have a perpendicular bisector. I don't do any constructions in this class because it's a little hard for you to see a ruler or a protractor and two-dimensional screen. I guess I can animate them, but I'm sure your instructor does an excellent job of explaining these constructions, and it's better to have those things right in your hands when you're using them anyway. I mean, I'm sure you already know how to use a pencil, but watching me use a protractor might not do much for you. Well, for bisectors, in addition to these two theorems, one that says that all the points on the perpendicular bisector are equidistant from the two endpoints, and the converse. These aren't completely outside of what you might expect. It kind of looks like that would be true, doesn't it? Well, what about this one? Wow. That doesn't even look like the middle to me. Does it look like the middle to you? Well, the funny thing is, if you draw your perpendicular bisectors, for each side, the point where they intersect is equidistant from all the vertices. That's kind of useful. I mean, anytime you have 3 points and want to position something so that it's no closer to any point than any other point, for instance, suppose you want to broadcast to 3 different towns. And you're here and out here. Well, you draw in your triangle here. And with any luck, you'd do a better job of drawing a triangle than I do. Now you draw in your perpendicular bisectors. this is a point which is equidistant from each of these towns. So no town would get a stronger signal than any other town. And if you wanted to do that, all you would have to know is your perpendicular, concurrency of perpendicular bisectors. That's a really long name for a theorem. Come on, guys, couldn't you come up with something better than that? Let's just call it the one that says that perpendicular bisectors intersect at the center of a triangle. At least that says what it is. Anyway, this is kind of a cool result. Well, it's useful, just like back when we looked at the cross members. If you have a rectangular frame and you include a cross member, the rectangular frame by itself was very unstable. Flop around, it wasn't worth much. You add a cross member and all of a sudden it's strong, it's stable. That's a useful thing to know if you don't like things to fall down on you. Well, this is a useful thing to know. Enjoy it. You don't get a whole lot of those in high school math classes. If this was a class in surveying, you'd learn a whole bunch of stuff that's useful. But you got to learn all this stuff so you can learn things like surveying and lots of other useful stuff. And here's something that goes right along with the fact that the circumcenter, I didn't tell you that word yet, did I? Well, naturally there's a name for this point where these perpendicular bisectors intersect. We described it by saying that that point is equidistant from all the vertices of the triangle. And of course, we have to have a name for it, so we don't just keep saying that point which is equidistant from all the vertices in the triangle. We can shorten that to circumcenter. And the word's not as bizarre as it sounds. If each of these points is equidistant from this point, pretty much the same as saying that they lie on a circle with radius equal to the distance from P to any one of these points. Why? Well, that's what a circle is. It's a set of all points which are equidistant from a given point, which is the center of the circle. So this point which is equidistant from all the vertices of the triangle is also the center of a circle which contains the vertices of the triangle. And any one of these, the distance from P to a vertex, any one of those could be called R, because they're all equal. And that's the reason for calling it a circumcenter, because this triangle is now circumscribed inside the circle, and the center of this circumscription, whatever you want to call it, is the circumcenter. Now I've been drawing these perpendicular bisectors inward towards the interior of the triangle, but there's nothing in the definition that says it has to just go inside. For instance, the way the bisector of this line is drawn, it takes off in both directions. Well, that's actually what happens. Why does that matter? Well, for one thing, think of these more as lines than segments. They just take off forever in both directions. And the important point here is, take a look. We've got a perpendicular bisector running out here, perpendicular bisector here, and another perpendicular bisector here. Now they intersect right here. That's not inside the triangle. Well, when we were talking about circumcenters and perpendicular bisectors, did we ever say they had to intersect inside the triangle? Nope. They don't have to. This is the point that is equidistant from all these vertices. This is the circumcenter. And we could draw a circle that would include each one of these points. In fact, I'll take a shot at that. Oh, here we go. There's a circle, more or less. Well, I don't draw all that well, but it actually does go through this point, and this point, and it's centered right here. So keep in mind, the circumcenter of a triangle doesn't have to be inside the triangle. Well, now that we know about perpendicular bisectors and circumcenters, let's start working some problems. What do we have here? P is inside ABC, and it's equidistant from the points A and B. On which of the following segments must P be located? Well, AB is just a line segment, right? Here's A, here's B. That's sort of a line segment. It's equidistant from points A and B. Here's A, and here's B. What do we know about anything that's equidistant from A and B? It lies on the perpendicular bisector. Remember, every point on the perpendicular bisector is equidistant from A and B. Conversely, every point that is equidistant from AB is on the perpendicular bisector. So, on which of the following segments must P be located? The perpendicular bisector of AB. Not sure where AC would even come into this. So, that would have been your answer. Well, here we have another one of those. Somebody made a mistake. Now, let's see here. This person says AB will pass through C. Well, certainly looks reasonable. Let's see what he did wrong. Well, they show here with these little marks. The diagram shows that AD and AE are congruent, which means this is a bisector. This little right angle thing here tells you it's a perpendicular bisector. So every point on this line is equidistant from D and E. Now, if this were an isosceles triangle, that would mean these two sides were congruent, and C would be equidistant from D and E, and therefore on the perpendicular bisector. This looks like an isosceles triangle, but that's the mistake. The diagram doesn't say it's an isosceles triangle. And if it was a fraction of a millimeter off, well, who would know? I sure wouldn't. So that's the problem. You can't just go by what you see. It has to actually be explicitly on the diagram. If the diagram looked like that, so that you knew these two were congruent, then you could say that C lie on the perpendicular bisector. You could also, even if those weren't there, let's see here, and you knew that these two angles were congruent, then you could say that C was on the perpendicular bisector, because our base angles theorem would tell us that this was an isosceles triangle, and therefore C is equidistant and lies on the perpendicular bisector. But we don't have any of those things given. So we don't know that this is an isosceles triangle. Yeah, this one's kind of messy. We've got that JN as the perpendicular bisector of MK. Find JK. Well, there's JK. That was easy. Wait a minute. They wanted something else, didn't they? When they write JK like that, that means the length of JK. Shoot. That means we have to do algebra. JN is the perpendicular bisector of MK. So right off the bat we can say that this, well, those two are congruent, but we can say more. this is on the perpendicular bisector, that is J, which means it's equidistant from K and M. So these two must be the same. So we can write 5y plus 8 equals 7y minus 6. Add 6 to each side and subtract 5y, or y equals 7. But they wanted the distance from J to K. 5 times 7 is 35. So that's what, 43? I think. Did I make any arithmetic mistake here for 14? Yeah, that's right, 7. Okay, yeah. I'll stick with 43. That's my final answer. Hope you guys got something close to that. That's all they wanted here. It's actually fairly easy. You just had to spot the fact that J lies on the perpendicular bisector. And that means that, well, that's where I told you that J was on the perpendicular bisector. You had to spot the fact that anything on the perpendicular bisector is equidistant from the two endpoints, and then use that fact to set up your algebraic equation. Here's another simple one. You'd probably just do this in your head. This line here, 59.6, same as this one. This one here, 195.5, same as this one. Well, how come? Well, let's consider this segment from here to here. Well, it's 40 meters on this side and 40 meters on this side. That would put this right in the middle. In other words, a midpoint. So we've got a line going through the midpoint right here. This is this big support thing. But this little right angle symbol tells us this is perpendicular. So it bisects and it's perpendicular. I think that makes it a perpendicular bisector. Every point on this perpendicular bisector is equidistant from the two endpoints. So this point here is 59.6 meters from this endpoint, then it must be 59.6 meters from this endpoint. And exactly the same argument applies here. This side is 40 plus 128. This side is 40 plus 128. So, once again, this line bisects it. It's perpendicular. So, every point on this vertical line here is equidistant from these two endpoints also. Means this blue line must be the same length as this red line. Boom, we're done. It took way longer to explain that than it did to write out the answers. You probably had it figured out in about 10 seconds, right? Well, here you want to find the spot that is equidistant from these 3 points. According to this, they're going to walk their dogs and they want to use the diagram. Well, you could take the diagram to somebody who's smarter than you and ask them to figure it out. That's one way to use the diagram. Suppose you don't know anybody smarter than you. Well, now you got a problem. You're going to have to do it yourself, aren't you? Well, if you had to do it yourself, all you have to do is consider each of these locations to be vertices of a triangle. Now, draw in your perpendicular bisectors. And you may have noticed by now that if you do it right, you only need to draw 2. The other one's going to have to intersect in the same spot, isn't it? You can always draw in a third one just as a check. Make sure you didn't make a horrible mistake. But this is how Mike and Ken and you could all make sure that you met up at a place equidistant. and nobody would have to walk farther than anybody else. Real easy. Well, this one wants you to, well, let's see here, what are they saying? They found these stones, which they think are part of a fire pit, and they figure the fire pit would be in the center. What does it mean to be in the center? Well, that's a good question. For a triangle, probably what you mean is the point which is equidistant from the three other points. Just like the center of a circle is equidistant from every point on the circle. So chances are what they want to find is a point equidistant from each of these rocks. So I went ahead and drew in some lines connecting these rocks so that they form a triangle. Now they're saying find the approximate coordinates of the point at which the archaeologist should look for the fire pit. Well, they asked for approximate. Well, anytime somebody says approximate to me, that means I can just draw a picture and guess. Don't have to do a whole bunch of messy distance formulas and algebra and come up with exact numbers. Yeah, saying approximate to a guy like me is dangerous. I will be pretty loose with that description. So, the next thing you would do, I think, draw in your perpendicular bisectors. Now, they say I eyeballed them. These aren't exact, and the fact that the intersection forms a little triangle and not just one point indicates that it's a gross approximation. But they asked for an approximate point. I would say the approximate point is right about there. And I don't know, what point is that anyway? Well, let's see here. This is y equals 6. Then this must be where y equals about 6.5. And let's see, 6, this looks like 7. It's like about 7.5. And in an application like this, it seems to me a diagram would be more than sufficient. After all, you're only guessing that the rocks were on the outside of the fire circle and equidistant. They could have been kicked around all over the place. So, in this kind of an application, I'm pretty sure that sketching it and being approximate is plenty good enough. So I'm guessing the approximate answer they're looking for is like 7.5, 6.5. That's what I get when I draw it in. And when they say approximate, well, you're free to do things like that, I believe. That's my interpretation of approximate. Here's one that's kind of strange. We've been using triangles, finding points that are equidistant from vertices of triangles. What about just a general old polygon? Do we have a way to find a point that's equidistant from all the vertices of any old polygon? No. If this line and this line were parallel, we might have something. These two kind of look parallel. And if they really were, we still wouldn't have much, because the perpendicular bisector here would take off like this. The perpendicular bisector here, even if they were parallel, they'd never intersect, since these are different lengths. For instance, you could redraw an actual If we had 4 points which, say, formed a rectangle, now we'd have something interesting going on. Well, sort of interesting. Maybe I'm easily amused. Wow. Suppose we had a rectangle. We could draw a diagonal and produce 2 triangles. And they'd be 2 right triangles. Suppose we drew in some perpendicular bisectors for each of these 2 triangles. For instance, here, if we had 4 points on a rectangle, we could draw in a diagonal. Now we have these 2 triangles. Let's find the circumcenter of these triangles. In other words, the circumcenter of this triangle would be a point equidistant from these 3 points. We draw a perpendicular bisector here, another one here. They intersect right here, and we draw a perpendicular bisector here. We don't have to draw much because we're already there. Same thing with this. We drop this down, and they intersect right here again, right on the hypotenuse. Well, that's not a coincidence. The circumcenter of a right triangle is always on the hypotenuse. Remember, at the beginning of this, I drew one, and kind of a weird triangle that went like this and like that and connected these, and the circumcenter was out here, right? That's because we had an obtuse angle. With an obtuse triangle, that is, a triangle which contains an obtuse angle, the circumcenter is outside the triangle. If all the angles are less than 90 degrees, that's an acute triangle, the circumcenter will be inside the triangle. For a right triangle, well, that's right between acute and obtuse, and the circumcenter kind of works that way too. It's not on the outside, and it's not on the inside. It's right on the hypotenuse, and that's always true. That tells us something about the rectangle. In fact, it tells us that the circumcenter of a rectangle is going to lie on the diagonal. Doesn't help us much over here, does it? We don't have a rectangle. We don't have a triangle because we got 4 points. Is there a point? For instance, I drew these two cross here. Is that? No, that's not it. I really don't see a way to find a point that's equidistant, at least not inside here. On the outside, well, I don't see how that would work, because whatever it is from here to here, it's going to be farther from here to here, isn't it? We don't have enough of a spread. See, with a triangle, it's different. We've got something like that. Well, if the circumcenter is out here, it could be equidistant from here to here to here. But the way this is set up, it wouldn't really make sense. I don't see anywhere to put this outside. Are there any obtuse angles in any of these? For instance, could we create any triangle which would have a circumcenter outside the triangle? Well, this looks obtuse. So this would have a circumcenter outside the triangle. On the other hand, this triangle is obtuse and would be inside this triangle. So as we find circumcenters for triangles, they're going to be in different places. I don't see where we're going to create 4 triangles and find the same circumcenter for any 2 of them and decide that that must be a circumcenter for all 4 points. The other thing we could do is try to draw a circle with these 4 points on it and see how that worked out. I gave it a shot and I couldn't draw a circle. I could draw an oval that contained all these points, but I couldn't find any way to place or draw a circle that would go through all of these points. So unless you have a parallelogram, that's another word for what this is, I don't think you're going to generally be able to find a circumcenter for 4 given points. That'd be like saying, given any set of points, can I always find a circumcenter? And the answer is no. You can't always find a circumcenter, which is part of what makes mid-segments so cool, because you can use them, perpendicular bisectors, cool, because you can use them to find a circumcenter. And again, that's a property of triangles, and that's another reason that we use triangles so much. They have lots of cool properties. And the ability to find a circumcenter to a triangle is one of the cool things about triangles. You can't just say that about any old polygon. Well, that's about it for this section.